So we have studied that particularly in the reaction turbines, the water is brought from the penstocks and then moves on to the moves, either it will be an inward radial flow or an outward radial flow, or maybe an Kaplan turbine. But we have seen that it is always the the runner is surrounded by an airtight casing. So what is brought from the penstocks and then moves on and then goes into the casing, and then from the outer circumference to the inner circumference, particularly in case of an inward radial flow turbine. So after the water passes through the runner, so here it moves on to the draft tube. So draft tube is this part. So draft tube is a passage which is connecting the runner exit to the tail race. Okay, is connecting to the runner exit to the tail race. So it is a pipe of gradually increasing cross-sectional area. So we have seen that the lower part of the draft tube is dipped in the tail race. Okay, so here it will be an atmospheric pressure here. So now since it is dipped and here we have atmospheric pressure, so finally here generally it is seen that the pressure at the inlet of the draft tube is always negative, so this will enable to keep the turbine at a higher level, or install the turbine at a higher level. So what are the functions of a draft tube? The functions of the draft tube is that by having the lower end of the tail race dipped in the water, so a negative pressure head is created. A negative pressure head is created at the outlet of the runner or at the inlet of the draft tube, so which enables the turbine to be placed above the tail race, so that so that it will be easy for repairs. And also by creating a negative head, so that means in turn it is here the net head on the turbine is also increased. So that's the advantage. And the other advantage is by making gradually increasing cross-sectional area, so whatever the kinetic energy rejected by the runner is converted into the pressure energy, okay, into the useful pressure energy, which is left into the tail race. So those are the functions of the draft tube, and that's why draft tube is to be provided. So this is the draft tube which is provided for a Kaplan turbine. So that's what. So in here and the I told you about the draft tube. So also now there are many types of draft tubes, like straight divergent type, also called as a conical draft tube. We also have a simple elbow type, or a moody spreading tube, or hydraulic cone tube, and or elbow type having a circular cross section at inlet, whereas rectangular cross section at the outlet. So these are the various types. This is known as a straight divergent tube, which is a conical tube. So also a simple elbow type, and this is the moody spreading tube or a hydraulic cone tube. So here the inlet is cross section, inlet cross section is circular, whereas here it is rectangular outlet. So I also told you about the various functions of the draft tubes. It serves as a passage for discharge of water from runner outlet to the tail race. It also permits a negative head to be established at the outlet of the runner or at the inlet of the draft tube. So thereby it will increase the net head on the turbine. So this also allows the turbine to install above the tail race level. It converts large portion of kinetic energy rejected by the runner to useful pressure energy. So coming to the draft tube theory, so we have, so this is the inlet of the draft tube, whereas this is the outlet of the draft tube. We have seen that the outlet of the draft tube is dipped in tail race. Let that vertical portion of the draft tube which is dipped in water or in liquid is, let it be y, and that the vertical distance of the inlet from the tail race, let it be hs. So now your total length will be hs plus y. So let the velocity be v1 at the inlet and velocity be v2. So also pressure be p1 at the inlet and p2 be at the outlet. Let hl be the loss between section 1 and 2 as flow takes place from section 1 to section 2. So by applying Bernoulli's equation between section 1 and section 2, we have P1 by rho g plus V1 square by 2g plus Z1. So here the datum is taken at section 2. So therefore Z1 is Hs plus Y. So therefore Z1 is Hs plus Y. So now the pressure here is P2. So there is P2 by rho g. Velocity is V2. So V2 square by 2g. But since the datum is at section 2, so Z2 is 0 plus the loss that takes place from section 1 to section 2, which is HL. So we can also write what is P2 by rho g. So P2 by rho g is nothing but here it is at the tail race, it is the atmospheric pressure. So it is Pa by rho g. As we move downwards, the pressure increases. So plus Y meters of liquid. So plus Y. So if you substitute this P2 by rho g as Pa by rho g plus Y here in this equation 1, so then we get P1 by rho g plus V1 square by 2g plus Hs plus Y. Instead of P2 by rho g, we can substitute this here and then plus V2 square by 2g plus HL. So now we can find that this Y and Y gets cancelled out. So P1 by rho g, P1 by rho g can be written as Pa by rho g. Hs is brought to this side minus Hs minus. So here this is minus V1 square. Okay, so minus V1 square. So minus of minus plus. So this is V2 square. So minus of minus is plus HL. So that means what this equation indicates? This equation indicates because from atmospheric pressure you are deducting this quantity as well as this quantity. So that means the here if the atmospheric pressure is 0, that means 0 gauge. So that means this will come out to be a negative pressure, that is negative gauge pressure. So therefore Pa by rho g is always less than the atmospheric pressure. So if you take Pa by rho g as 10.3 meters of water, then you will get plus answer, which is an absolute pressure. But in terms of gauge units, so it is always negative, so always lesser than the atmospheric pressure. So this equation only will indicate that P1 by rho g is always negative. So these two equations are used in solving the problems. So we'll take up draft tube theory problems and see that how should we calculate Pa by rho g, or how to calculate depth of immersion, that is Y, or to calculate length of or Hs, that is what is the portion that is above the tail race. So now you know that when we are using the this draft tube, so therefore since the velocity is more at the, because the diameter is less at the inlet, whereas the diameter is more at the outlet, so there will be definitely the loss of kinetic energy. So here the efficiency is nothing but output by input. So output is nothing but the loss of the loss of kinetic energy, or it is actual conversion of kinetic energy to the pressure head divided by the kinetic. So loss of kinetic energy is here at the inlet is V1 square by 2g, out the outlet is V2 square by 2g. So there is some loss taking place. So therefore it is nothing but V1 square by 2g minus V2 square by 2g minus HL divided by the original kinetic energy that is at the inlet, that is V1 square by 2g. So now we take a problem. So a water turbine has a velocity of 6 meter per second at the entrance. So V1 is 6 meter. Similarly, V2 is at the outlet, it is 1.2 meter per second at the exit. For the friction loss of 0.1 meters and the tail water 5 meters below the entrance to the draft tube. So this will become Hs. You have to find pressure head at the entrance. Now it is given that velocity is 6 meter per second. So V2 is 1.2 meter per second, loss is 0.1 meters. So whereas this is given, which is 5 meters. So now taking datum as section 2, so Z1 will become Hs plus Y, Z2 will become 0. So apply Bernoulli's equation between section 1 and section 2. We have P1 by rho g plus V1 square by 2g plus Z1 is Hs plus Y, where equals P2 by rho g plus V2 square by 2g, Z2 is 0 plus loss. So instead of writing P2 by rho g, I will write atmospheric pressure head, that is Pa by rho g plus Y. So as we move downwards, pressure increases. So this is how it's, so we can cancel out Y and start substituting. So you need not write this equation. So instead of writing this equation, Now we want to calculate P1 by rho g. You substitute the value of V1 as 6 meter, 6 square by 2 into 9.81. HS is 5. So PA by rho g you can substitute as 0. PA by rho g as 0. 0. V2 is nothing but 1.2, so 1.2 square into 2 into 9.81. HL is 0.1. So by solving this, you will get minus 6.66 meters gauge. So therefore, pressure at the inlet is always negative. So if you take PA by rho g as 10.3 meters, then you will get positive answer. That means you will get 10.3 minus 6.66 as the answer, which is absolute pressure. So it's better to always calculate as the vacuum pressure or the negative pressure by putting PA by rho g as atmospheric pressure, which is 0 gauge. Taking another problem, a conical draft tube having diameter at the top as 2 meters. So now the diameter of the inlet is given and pressure head at the inlet is also given, which is 7 meters of water vacuum. Vacuum means minus 7 meters of water negative. So it discharges at the outlet with so that means V2 is given 1.2 meter per second, but the discharge is also given, which is 25 meter cube per second. So losses has been neglected, so therefore HL can be taken to 0. We have to find the length of the draft tube. So what is the length which is immersed in water? So immersed in water is nothing but y. So we are required to find the value y, whereas the total length of the draft tube is given. So knowing the diameter 2 meters at the inlet, whereas the pressure is, again don't forget to write minus sign. So you have to write, because it is vacuum pressure, then negative pressure minus 7 meters. So velocity at the outlet is given. Knowing the discharge, we can find the velocity at the inlet. So because velocity at the outlet is known, only thing is we have to find velocity at the inlet, which gives discharge divided by area. So now writing Bernoulli's equation, we have P1 by rho g plus V1 square by 2g. So this Z1 is Hs plus y. P2 by rho g plus V2 square by 2g. Z1 is Z2 is 0 and plus loss is also not given, so 0. So here in this case, P2 by rho g can be written as atmospheric pressure head plus y. Okay, so don't cancel this, because we know that length of the draft tube is given, which is Hs plus y. So directly you can substitute 5 meters. Here P1 by rho g is the head, that is minus 7, directly you can substitute. So velocity is calculated V1, so you can substitute. So here also we are required to find y, so keep as it is, don't cancel out, otherwise you have to find h and then deduct from here. So instead of doing that, it's better that you keep Hs plus y like this, put it as 5 meters and then start calculating for y. So y will be 1.1536 meters. So a conical draft tube having inlet diameter, that is D1 is 1 meter, whereas D2 is 1.5 meters, and discharges at the outlet. So V2 is given, which is 2.5 meter per second. Total length of the draft tube, which is Hs plus y, is 6 meters, whereas y is 1.2 meters. Loss of head is given, which is velocity at the outlet. Outlet velocity is V2, so therefore it is 0.2 times V2 square by 2g is HL. So we have to find pressure at the inlet, which is P1 by rho g, and also we should find efficiency of the draft tube. So given this data, D1, D2 and velocity at the outlet, and also the length of the draft tube is given, and that is immersed in water is also given. So HL is, as I told you, it is 0.2 times V2 square by 2g. So now you can use continuity equation, which is A1 V1 equals A2 V2, because the diameter of the inlet as well as diameter of the outlet are given. So now velocity at the inlet has to be determined by using velocity at the outlet. So that gives velocity as 5.625 meter per second. Now apply Bernoulli's equation, which is P1 by rho g plus V1 square by 2g plus Hs plus this is Z1. Similarly Z2 is 0. So instead of P1 by P2 by rho g, you write it as PA by rho g plus y. So don't cancel out all these terms, because Hs plus y is 6 and y is also given. So here in this case V1 is known, V2 is known, and even HL is 0.2 times V2 square by 2g here. So you can find out the pressure head at the inlet, which comes to about minus 6.03 meters of water. So efficiency can be calculated. Efficiency of draft tube is nothing but loss of kinetic energy, which is V1 square by 2g minus V2 square by 2g minus any loss that takes place divided by the original kinetic head into 100. So V1 is known, substitute as 5.625, V2 is known, which is 2.5, and also the loss is 0.2 times V2 square by 2g. Because V2 is 2.5, you can always calculate. So then substitute the quantities and find out the efficiency of the draft tube, which comes to 76.3 percentage. So these are the problems associated with the draft tube, and the concept of draft tube should be very clearly understood. Why the draft tube is provided, and what are the types of draft tube, and the functions of the draft tube. As I was discussing in the turbines as well as in the draft tube, we have found that at the inlet of the draft tube always pressure is negative. So, and also at the runner exit also the pressure will be negative. So therefore there is a chances that whenever the pressure of the flowing liquid is less than the vapor or reaches vapor pressure, then the vaporization of the liquid takes place. So liquid starts boiling and vapor bubbles are formed. So these vapor bubbles are carried with the flowing liquid to the high pressure zones where they collapse. Or the vapor bubbles collapse, and due to the sudden collapsing of the bubbles on the metallic surfaces, so high pressure is produced, and the metallic surfaces will be subjected to high local stresses, and because of this the surfaces will be damaged and the cavities may be formed on the metallic surface, and this process is known as cavitations. So in also we have particularly in the hydraulic system, wherever the pressure reaches the vapor pressure, such type of process phenomenon will be formed known as cavitation, because once it reaches vapor pressure the liquid will start boiling, or it may get converted into vapor bubbles, and these vapor bubbles are carried to high pressure region where they collapse, and because of this collapsing of the bubbles there will be a very high pressure, or the metallic surfaces will be subjected to high local stresses and the surface will get damaged and the cavities are formed, and therefore this is known as cavitation. So where does it happen in particularly in the turbines? So in the turbines it happens only in the reaction turbines, because in the reaction turbine there is a chances that the negative pressure will be at the draft tube level, that is the inlet of the draft tube, or at the runner exit, where the pressure is considerably reduced and may reach vapor pressure. So due to cavitation, here what happens is metal of the runner vanes or the draft tube is generally damaged due to the cavities that are formed on them, which may result which also results in the lowering of the efficiency of the turbine. So what precautions do you take against cavitations? So now since you know that the pressure of the flowing liquid in any part of the hydraulic system should not fall below the vapor pressure. So when it falls below the vapor pressure, then vaporization of the liquid takes place and liquid starts boiling and vapor bubbles are formed. So therefore we have to take care that in any hydraulic system or maybe in turbines, the flow the absolute pressure should not be below 2.5 meters of water. That is, absolute pressure should not reach 2.5 meters. So that means in gauge pressure it will be 2.5 minus 10.3, so about minus 7.8. so in the problems we saw that it was somewhere around minus 6.66 or minus 6.03, something like that. So nowhere it should reach around 7.8. If it reaches 7.8 meters, minus 7.8 meters of water or 2.5 meters of water absolute, then this cavitation process takes place. So that's why this is the precaution that you should take care that so nowhere absolute pressure head should be below 2.5 meters of water. So you can also use special materials or the coatings such as aluminum or a bronze or stainless steel, which are generally cavitation resistant materials, and by using this you can try to have precautions against cavitations or cavities to be formed, or the metal may not get damaged. So coming to the last part of the turbine, which is known as the speed. I've already told you that a specific speed is the speed of geometrically similar turbine when working under head of 1 meter will develop 1 kilowatt power. So therefore it is given by the equation n root p divided by h to the power of 5 by 4. So what is the use of specific speed? By use of specific speed, that when you try to build a model and try to operate on a head of 1 meter, it will develop 1 kilowatt power, but the corresponding speed that is achieved is known as specific speed. So if specific speed is around 8.5 to 30, then it is a single jet Pelton wheel. So if it is between 30 and 50, then it is multiple jet Pelton wheel, or it is between 50 to 300, say this is a Francis turbine, and anything around 300 to 800, 850 backup plant turbine. So that you can, knowing the operating speed or a power developed, or where it is working under a particular head, then you can find specific speed and state what type of turbine can be is being used. So now, using the basic equations of that what we used in the turbines chapter, so we have what is known as a specific speed. So specific derivation for specific speed. So we have what is known as overall efficiency. Overall efficiency is P by that is the shaft power divided by the water power. So water power is WQH. Now what is power? So power is the overall efficiency into W into QH. Now since overall efficiency and specific weight is a constant, so P is proportional to Q into H. So this is first equation. So you also know that V is equal to CV root 2 GH. So therefore V is proportional to root 2 GH. Also we have something like the speed ratio, or something like U is equal to speed ratio times root 2 GH. So U is also proportional to root H. So therefore we can state that U is proportional to V. So since V is root H, so you can say that U is proportional to root H. That's the second equation. So now you also have U is equal to pi dn by 60. So since pi and 60 is constant, so U is proportional to dn. So since U is proportional to root Hn, so root Hn will be proportional to dn. So therefore we can get an expression for D, where we can state that D is proportional to root H by n. So this D can be used in the area. So therefore we write an expression for discharge, which is area into velocity. But you know, in Kaplan turbine, area is nothing but pi by 4 d square minus small d square, where hub diameter is also expressed in terms of outer diameter is 0.35 capital D, something like that. So therefore ultimately it will be in the d square. So area is proportional to d square. So therefore you can write as Q is proportional to d square into, because velocity is proportional to root h, you can write it as root h. So instead of d you can substitute this here. So what is d square? It is h by n square. So h by n square is substituted. So that gives h into h to the power of half is h to the power of 3 by 2 by n square. So take this value of q and substitute here. So that is, so now you are substituting, that gives 3 by 2 plus 1 is 5 by 2 by n square. So that means taking out the proportionality and introducing a constant. So P is equal to K into h to the power of 5 by 2 by n square. Now use the definition of specific speed. According to definition of specific speed, when h is 1 meter, the power developed is 1 kilowatt when the speed is specific speed. So therefore substituting P as 1 kilowatt and K is a constant, so which is to be determined. H is 1, therefore the corresponding speed N becomes Ns, so Ns square. So what is the value of K now? So K will be equal to Ns square. Take this and substitute here. So it is P equals Ns square into h to the power of 5 by 2 by n square. So therefore what is Ns square? It is n square P divided by h to the power of 5 by 2. So taking square root on both sides, specific speed is n root p h to the power of 5 by 4. So this is how you derive the specific speed using the various formulas and the relationship between each of the parameters. We know that taking a problem, a turbine is operating under a head of 25 meters. The speed is 200 rpm. So therefore discharge is 9 meter cube per second. Then since you know oral efficiency, which is 90%, so we can find the power. So by using oral efficiency, which is P by WQH. So now oral efficiency is 0.9, 90%. Specific weight is 9810. Discharge is 9, whereas head is 25. So we get this answer in watts. Dividing by 1000, we'll get 1986.525 kilowatts. So you know that in specific speed we have to always substitute P in kilowatts. That's the reason it is converted into kilowatts. So substitute here. So the operating speed is 200 rpm, whereas H is 25. So we get 159.5 rpm. Since the specific speed is between around 50 to 250, so the type of the turbine is Francis turbine. So this is how you can identify the type of the turbine to be used. So here depending upon the speed and the head, so we can find out the power developed, and using in specific speed you can find out what is the type of the turbine. So if this answer was somewhere around 400 or 410 rpm, then it would have been the Kaplan turbine. Okay, so like this we have various problems uh, to be done and identify the type of the turbine. So this is about the Kaplan turbine, and also the basics of the draft tube theory was discussed, and also the specific speed and why it is used was discussed in detail. So this is about the turbine chapters, and we end this session on turbine chapter, and hope probably I will take one more session for inward reaction flow turbine, where I will cover some problems on inward radial flow turbines. The concept of inward radial flow turbine also will be discussed. So hope you had a nice session. So these all these chapters which were covered under turbines will be helpful for you for gate examinations, or as well as for the competitive examinations. Maybe for some interviews there will be the concepts of the turbines can be asked, and you should be better prepared with the concepts of, particularly we had more concentrated on the impulse momentum equations, and used in order to find the force exerted also, and also the work done per second on the turbine. Thank you very much for this session, and hope you will have a better study on all these chapters that I have uploaded on my YouTube channel. You can subscribe to my